Hi, this talk is called Compiling Containers. I'm going to talk about how container images are made. I'm going to talk about this tool that I think is pretty cool called BuildKit. I'm going to teach you a little bit about compilers and do a code demo and talk a little bit about the future of containerization and cloud native stuff. So I hope you enjoy it. I'm Adam Gordon-Bell. I am an open source software developer. I am a Canadian. I am a podcaster. I have a podcast about software engineering. You can see there on the right if you want to check it out. Just search for my name in your podcast player. I'm a developer advocate at Earthly, where we are trying to improve builds. I'm not going to talk about Earthly too much today, but you should check it out, earthly.dev. So you've probably heard a lot about container runtimes in recent history. Kubernetes stopped using Docker shim and started using CRI shim. A lot of people freaked out, but really there's a lot of these runtimes. You can see a bunch of them here: runc, containerd, etc. It doesn't really matter the various functionality of each of these for the talk today. I'm going to be talking about container images, OCI images to be specific. All of these container runtimes can run OCI images. And what I want to talk about is how you make this image, how you make the image that turns into a running container. And we're going to get a little bit down in the weeds about how that is done. So just a little background information. You probably know what a container is. It's like a virtual machine, except you share the operating system kernel and some other stuff, so it has lower overhead. It's like the 10-second version. But do you know the difference between a container and an image? So the way I like to think about it is via analogy. If you think about an executable is a program that you can run on your computer, and when you launch it, it becomes a process. And you can launch as many processes as you want from that single executable. Similarly, an image is something that's not running. And when you run that image, it becomes a container, and you can run many containers from a single image. So sort of an executable is to an image as a process is to a container. You could imagine a virtual machine fitting in this as well. An image is like a VM image, a container is like a running VM, except that when you make changes to a running VM, you can save them back to the image. With a Docker image, they are immutable. So any changes that happen while it's running won't actually affect the image. So that executable turns into a process, but how do we get that executable? To get the executable, we use a compiler. So here's an example. I have this hello world. It's written in C. You can see it here on the left. I'm going to pass it to a compiler. I'm going to use LLVM with the Clang front end. Hello world, as an example, comes from this book, The C Programming Language by Brian Kernighan and Dennis Ritchie. And I mean, we're still using this as an example today in many languages. So I'm going to compile it to x86, and my x86 ends up being like this code we see here on the right, which is x86 assembly. This is the assembly code for what will be executed when you run this program. Assembly code maps basically one-to-one to machine code, which is binary, which we're not showing here because it's much harder to read. But the machine code is what actually is executed on your CPU. It's what your CPU architecture understands. So the Docker equivalent of this simple hello world program is something like this. So we have from Alpine, we're going to copy in a README file, and then we're going to echo some results to a file called build.txt. So to compile that, we use Docker build. So we Docker build dot, which is our present working directory, and then we're going to pass it -t to tag it test. So creating an image from a Dockerfile, it sort of works the same way as our hello world example. The Dockerfile is passed to BuildKit along with the build context, which in our case was the present working directory because we used dot. Generally, each statement is turned into a layer as part of this build step, and those layers are packaged up into an image. One thing that's different from a traditional compiler is that with the compiler, you're just taking the source code. But Docker builds, you're actually taking the file system context. And that's how you can do things like this copy command, because you can take things from the file system that are referenced when you pass it in. So in this case, we pass in our present working directory, and we use that to copy in files. So comparing our C compiling to our Docker building, we can see how they look quite similar, right? You have the same type of steps, starting with your input. You have the compiler, which is LLVM or build kit, and then you end up with your executable or image. So what is build kit? This is build kit, and it is kind of the brains behind Docker build. And it drives not just Docker build, but a number of interesting cloud native projects. One is Open FAS, Open Functions as a Service, which, as I understand it, is a project to run serverless functions on Kubernetes. There is Rancher Rio, which is an application development engine for cloud. And there's probably tens of other projects that use BuildKit. And BuildKit's what we're going to dive in a little bit today. I want to give you intuition for how these images are made, which I think could be pretty useful. But first, let's talk a little bit more about compilers. So earlier I had this diagram again with the hello world, and we generate this assembly. Saying compilers work this way is kind of a lie. It's a simplification. So on the left here is the PDP-11. That is the first computer that a C compiler existed for. That compiler was written by Dennis Ritchie. And the simple diagram that I showed earlier, that actually is exactly what would happen on the PDP-11. The C code would be taken by the compiler and it would be converted into PDP-11 assembly instructions. But this is direct mapping. It poses a problem. Whenever you have a new machine, it means you need a new compiler. And what language do you write that compiler in? The first C compiler, as I said, was written in PDP-11 assembly, but you don't want to have to repeat that for every new machine architecture, for every new CPU. What happens when the VAX 11 comes out, or the new Apple M1 that you see here on the right? So this problem was very quickly solved by compiler authors who came up with this structure. They said a compiler can be split into stages. You have a front end, you have an optimizer, and you have a back end. The front end takes in your source, your various files, and tokenizes them and parses them, builds an abstract syntax tree. The middle is the optimizer. It could do performance optimizations to make your code faster. At some point, they called this middle the middle end, which I'm glad that term didn't catch on. And then you have the back end, which actually generates the actual assembly. Now, the beauty of this approach is you don't need to build a new compiler for every machine architecture. You can just build a new backend. So this will all relate to Docker images, trust me. But the trick here is to get all the backends speaking the same language. For that, you need an intermediate representation. You need a language that's not C, but isn't assembly either. You need something in between. So once you have that language, and with LLVM, it's called LLVM-IR, which is the intermediate representation. All the backends then need to do is translate from that intermediate representation to the machine architecture that's specific to where they get things to run. But once you have that, you can have multiple front ends as well. So this is modern LLVM. This is sort of what it looks like. It started with the Clang front end. Now it has many front ends, right? It has Rust front end. There's a Go one. There's Julia. There's all kinds of different front ends. There's been sort of a Cambrian explosion of ahead-of-time compiled programming languages in the past 10 years. It's a result of how easy it is to add a front end because of this architecture that LLVM has. And the reason is that this is just a common interface between the various layers. It becomes sort of like a protocol. On the back end, we have not just x86 and ARM and RISC and PowerPC, but we also have a WebAssembly backend, which means you could take your Julia or your Rust and I guess compile it to run in your web browser. There's even GPU backends where you could compile your code to run on pixel shaders. You can build a front end as well, right? So if you can create a front end that translates this LLVM IR, you have a new programming language. Everything else, all the support for all these various backends is taken care of. So this is super cool. And the secret is just this intermediate representation. The front ends need to emit it and the back ends need to consume it. So bringing it back to container images, BuildKit works the same way. It has something called LLB IR, which is low-level builder internal representation, because containers need to be able to run on lots of machine architectures as well. And once you have the IR for varying backends, you can start having varying front ends as well. So right now, there's not too many front ends. Probably the most commonly used are just the various versions of the Docker syntax. There's Docker v1, Docker v1.1. But as I mentioned, there's OpenFast, there's BuildPack, there's some other things. But it doesn't have to be that way. So just to explain how it works, LLVM IR looks like this on the left. It's sort of a verbose and explicit programming language. LLB is much simpler. It looks quite different. With LLVM, the basics are kind of a simple programming language. With LLB IR, it's sort of a language for creating these self-contained cloud-native packages. So let me show you how that works. So let's start with building just a simple Dockerfile, and then we'll go from there. So this is the one we showed earlier, just from Alpine, copy README, and we're going to echo this to a file. So I can build this just like this. I'm going to tag it test, build the file, and then we can run it. So we want it to be interactive, and we want to run test, and we're going to open a shell. All right, so now we're inside of it, and we can see in this program, standard Docker build. Exit. So let's now take this file and just build it with BuildKit instead. So I'm on a Mac, so to do that, I need to do brew install BuildKit. I already have it installed, but if you're on a Mac, this is what you would need to do. And that gives you this new command called buildctl. You can kind of read through what it does there, but it lets you build things. But when it builds things, it needs to communicate with this backend that'll make the gRPC requests against BuildKit D. So we actually need to start that up. Let's actually make sure I don't already have it running. Okay, I don't. So this is how I would start the backend part of BuildKit. It just runs as a container. It's called Moby BuildKit, and I'm just going to call it BuildKit. And then you can see that here. And then I'm just going to tell buildctl where it is by doing that. So now it knows it is running as a Docker container, and then it has this name. Actually, that is incorrect. That should say BuildKit, right? So I actually want that, I believe. Let's see how it goes. So once we have that running, then we can try to build this using BuildKit directly. So using BuildKit directly is a little bit more verbose. So let's clear this. So you can just use it like this. So I'm going to use buildctl. I'm going to call build. I can specify which front end that I want to use. I'm going to use the v0 syntax. Specify the context. That's like where I can copy in files from for my copy command. Yeah, I specify my Docker file, which is in my present working directory. And then here we're giving it some output options. So we want to output as an image. This is specifying the backend that we showed earlier. There's a couple different backends. I can just make a tar file or whatever. So here, front end, here backend. I'm going to give it a name and tell it to push it. So I'm going to actually push it to Docker.io agbell.test. So let's run that. And then, so we pushed it there. Let's test by pulling it. Test. Actually, you know what we should do is change this here. So let's call this BuildKit built. Let's run this again so that we can differentiate. And then we'll pull it. And then we can run it with Docker run. It was called AGBL test. And then we want to open a shell. And then if we look at our build.txt, there we go, buildkit built. So we just built this file using buildkit directly. So now we're getting somewhere. So let's do something a little bit more advanced. If you remember, let's open up a new file. The way that buildkit's working is you have like your front end, and it's going to send LLB to buildkit, which to like the buildkit daemon, which can send LLB to backend. So let's just inject ourselves here. Let's programmatically build a front end. So to do that, all we need to do is build up this LLB and then send it. And LLB is specified as a protobuf. So you just have to make like a gRPC request with like, here's my protobuf. So I put together an example here. So you could do this in any language where you have support for protocol buffers. But what I've done is I've used Go, and that's because buildkit itself is written in Go, and they have the nice client library that I can just pull in, and that gives me the easy ability to put these together and see the various operations, and even dig in and see how it works if I'd like. So this is just my translation of our original Dockerfile. So we're going to come from an image that is from Docker.io library Alpine. You notice it's a little bit more explicit. I need to copy in a file from my context, which I'm going to specify. I'm going to copy my README and name it there README. And then I'm going to do a run. The run, you can see, is a little bit more explicit too. Back here, we just have echoes. Here we have to wrap it in a shell. And that's because like these commands, like echo and sending it to a file, like those are shell commands. So we need to run it inside of a shell. Okay, so this will generate all of our LLB. And up here in our main program, all we're doing is just writing it to standard out. And the reason is we're going to use buildctl to kind of make this happen. But first, let's just take a look at what we get. Yeah. So we can just run this, and we just get all of the protocol buffer contents to standard out, and it's a binary format, so not super readable. But what we can do is take it. Let's clear. What we can do is take that output. We can send it to buildctl, which has a command called dump llb, and then we'll pipe it through JQ, and we should get something more like a JSON formatted. So now we can kind of see this is the raw commands that we are sending through. So this you can see is our run command. We should be able to see, here's our copy, source and destination. Should have our context. Yeah, here's our local context that copy from will run. Here's our from. So that's kind of what the raw LLB, well, I guess this is the formatted LLB, looks like. So now let's just try to build this. So I'm going to do this. No, we haven't built it yet. Let's start with building it. Let's see. So we'll clear. So same idea, we're going to pipe it to buildctl. We're going to pass it this local context, but now we're telling it to output an image and call that AGBL test and push it. If you were like using this, if you wanted to build a more robust solution, you might want to have this application actually, find out if build kitd was running, maybe start it up if it wasn't, maybe have some error checking and whatever. But this is a nice way to test it out. We just rely on this buildctl tool to to handle all of that for us. So this should be building our program. There we can see it running right there. And then just, we can pull it down just to make sure that it actually pushed it. And then same idea, we can do docker run it HBL test, and let's run a shell. And then inside the shell, what was our file? Build. What do I call it? Built instead of build. There we go, programmatically built. So that image will run anywhere where you have a container runtime. So I think this is cool because by popping into a programming language here, rather than using a Dockerfile like this, if you need to do some things that are very complex, you have all the kind of control flow and structures and libraries and things that a programming language brings you, right? You can kind of raise the abstraction up. You could use it to get rid of duplication. I think it could be an interesting solution depending upon your use case. But, you know, like a front ends are actually usually more complex than that, right? Like a front end usually, instead of just sending LLB, it's usually more like taking in source code, which would be our Dockerfile, and, you know, like turning it into tokens, and then parsing those into an AST, right? And then generating the LLB and sending it on. So let's try something a little bit more like that. That might actually take a little while. So I put together a little bit of a example front end. So if you, did I share this already? If you look in this repo, you'll find it. It is here in this IC file subfolder. So this is an IC file. This is my own front end that I put together for Docker. Docker has this syntax when you call Docker build. If you specify syntax and then the name of a publicly accessible Docker container, it will pull this down and it will use it as the front end for building things. It'll expect it to take the source over gRPC, to parse it, to tokenize it, I guess tokenize first and then parse, generate the LLB, and then send that on to BuildKit. So that is pretty cool because you don't even have to have people install anything. Docker will pull this down if you just specify this. So I built my own front end, which I'm calling an IC file. It's more of a proof of concept, but there exists this language called intrical, which is from the 70s and was kind of built as a joke. And I think I thought it was kind of humorous to build a front end for Dockerfiles that looks somewhat like intrical. So mainly it does all the same things as a Dockerfile, it just uses different words. So instead of from, we have come from. Instead of copy, you use stash, which kind of stash the files inside of your container. Instead of run, you use please, which is just more polite. Intrical was known for its please statement. So in intrical, you could either say do or please do. And if you didn't say please enough times, then the compiler would say like, sorry, your program is not polite enough. I won't compile it. I think if you put too many please statements, it would also say your program is too polite. Anyways, it's just a proof of concept, just for fun. But now that we are building a complete front end and putting it in a Docker container, we can actually build without even using BuildKit. Well, without using it directly, I guess. So let me show you what that might look like. Okay. So I guess first, let's change it to my IC file folder. And then it's just the standard Docker builds. But we need to specify the file explicitly because it's not used to having something called an IC file. And we'll tag it IC1. So we can build that. Just standard Dockerfile. No buildctl required. And then we can do the same thing. We'll pull it. What did I just call it? Oh, I guess I didn't push it. So I think we can just run it. So we want interactive, we want to run ic1, and same thing, let's get a shell. And here we are inside of it. We can take a look, and if we look at cat.built, we can see custom built front end. That is our image. So we have just built our own syntactical front end for Docker files. I don't recommend you actually use this, but I think it is a nice proof of concept. So if you wanted to build your own syntax on the front end for a Docker file, this project could be a good place to start. What I did is I took one of the existing front ends for Docker and I yanked it out. So you'll find in here all the parsers for parsing the lines. You'll find the conversion steps for converting from the Dockerfile syntax to LLB. You will find the various commands for starting it up. But the main thing that I did was just look at the mapping for terminology to features, and I replaced the existing commands with the intercal style keywords, such as using stash for copy, or using please for run, or health check is are you okay? Anyways, it's a fun little example that just shows some of the things that you might be able to do with these tools. And that concludes the demos. So I think this is pretty neat, but you might be imagining like, who cares? We can create our own backends and front ends for containerization, but why would we? Well, these examples are just proof of concept, but you can do real things with this. Something you could do is like build your own AWS LAMBDA clone, right? Like use the programmatic functionality that I was just showing earlier, where you can build a service that takes in JavaScript. Maybe it just takes in a post request with some JavaScript and then programmatically builds a Docker container with that in it and ships it off to Kubernetes. That would actually not be that hard, right? As a proof of concept, you could probably do that in a couple hundred lines of code. You could also just build a specific image format for your org. This is called a Mocker file. The creator noted that Docker files in his organization were mainly just a list of a whole bunch of things that you need to call, like apt get on. So like you see this commonly in Docker files. One thing you can do is like put one per line, but then just because of the way that Docker images get built, you end up with a whole bunch of layers. So the thing that happens more commonly is you build just like a giant line that has like all these installs on it. That's kind of a mess, right? So Mocker file, which is specified in YAML, you just provide a list of packages, and the Mocker file will install each of these packages by just issuing those LLB requests. This Mocker file is specified in YAML, which I don't know. Depends. Sometimes I like YAML, sometimes I don't. But I think it really works for this use case. It nicely constrains the problem down to exactly the things that that needed to be done for many Docker image creation tasks. The other thing you could do with BuildKit, and this is probably my big message, is I don't know. Let's figure it out. Well, we can't know what we can create until we do it. When LLVM was created, like Rust didn't exist and Swift didn't exist and Julia didn't exist. There was no pixel shader backends or WebAssembly. But these things were all enabled by it existing. And now we have this tool for creating cloud native workflows. What should we do with it? I work on this project called Earthly. We use some of these BuildKit features for doing pretty cool, like reproducible builds, like CI pipelines. But I want to see more projects using it, like building on these foundations. On a historical scale, I think we're really early in cloud computing, so we get to kind of decide what the future looks like. So your name here, your project here, what can you build with this? Oh, and one other thing, this kind of 3-stage compile solution is super useful. Compiler problems are hidden everywhere. And when you spot one, there's like a whole literature of how to solve compiler problems. So if you recognize something you're facing is actually a compiler problem, all of a sudden there are all kinds of tools you can use to solve it. There's more stuff about BuildKit that I also didn't get a chance to cover in the demo. It's more than just an old-fashioned compiler. I've shown you how you can add front ends for it, but you might have noticed you can do that without requiring anybody to install things. You just have to reference the container it's in, because it unsurprisingly uses Docker containers for the different parts of its structure. But that's not all, right? A traditional compiler is usually a pure function, kind of, where it takes in all the source, does some stuff, and produces an output. But BuildKit, it does more than that. It has workers, which power a feature called Docker BuildX, which let you build a single Docker image for many machine architectures at once. You can run multiple architecture backends at the same time. And also, it has really advanced caching. It's very cache efficient because it's expecting things to be called repeatedly. And so it can keep track of what steps can be skipped and replay them. Think about it like kind of like an incremental compiler. Like I worked in Scala for a long time. The compiler was super slow from a cold start, but when you were incrementally building things, it was super fast. So BuildKit is kind of built from the ground up to be aggressively incremental. Another thing is it's concurrent. Anytime you build something, we can kind of look at the structure of what you're building, determine what steps depend on others, and BuildKit will run them in parallel while it can. And the coolest feature is probably that it can be distributed. Because you're using gRPC between these layers instead of just like a C API, like a standard compiler might use, it's trivial to actually have a cluster of these things, right? You could have a whole bunch of workers and they could be running on different machine architectures, or they could just be all on the cloud so that you can distribute your workload and you can distribute out the work that way. So I think that is like super neat. So I am Adam Gordon Bell. This was my talk. You can find me basically anywhere by searching for that name. I'll share the links to the source for the examples. Build something cool using BuildKit and let me know about it. If you're looking for inspiration, you can take a look at Earthly. You can find it on GitHub or at earthly.dev. Thank you so much.